Okay, good morning. This is Professor David J. De Los Reyes. Okay, the date for today is November 25, 2023. In time is 1:54 a.m. Okay, my subject matter for this morning will be a continuation of my AC machines, and we are now on lesson number 62. We are running smooth. We are on the topic alternator. Alternator, we are on the so-called power generation. The machine that produces our electricity at home are actually located at the power generation side, at the dam side, at the nuclear side, or at the wind turbine side. Okay, let's proceed. The subject matter for this morning will be AC machines, lesson number 62, and the title of the topic will be Alternator regulation. How do we compute alternator regulation? If under the study of transformer there is a so-called transformer voltage regulation, just the same under the study of alternator there is the so-called alternator regulation. Alternator regulation refers to the what we call this voltage regulation. It refers to the voltage generated by the alternator. Could it maintain a what we call this stable generated voltage for any type of loading condition maybe? Okay, let's try to bring out the formula on how to compute the voltage regulation or how efficient the alternator could generate a stable voltage. BR is equal to B with the subscript NL, meaning no load, minus B with the subscript FL, meaning the voltage at full load, all over the voltage at full load. This is multiplied by 100%. This is on the basis per phase value. So in order for us to use this formula, the values of the voltages involved here will be on the per phase basis. It's not on the terminal voltage or the line-to-line voltage. It should be the per phase voltage of each winding. For this to be correct, it should be on the per phase value. Where the designation BR is a voltage regulation, capital letter V, victory, with the subscript NL, meaning the voltage at no load. Oh, this is actually per phase. Of course, we'll place this per phase so we don't make a mistake. Capital letter B, victory, with the subscript FL, meaning full load, will be the voltage at full load. This is per phase. Okay. Of course, when a generator is operating and the terminals are open, there will be no load connected at the terminals. Of course, the resulting current will be less, so the voltage drop on the armatures will be less. So actually, the terminal voltage at no load is actually high. Okay, but at full load, it will be greater. Okay, because to maintain that voltage and due to the reactance and resistance drops on the armature, which must be compensated, okay, at full load we should generate a greater voltage to maintain that same terminal voltage. Okay, let's try to bring out an example problem on how to compute alternator regulation. Oh, this is an AC one now because under the study of AC circuit, what do you call this? Is it AC circuit? AC machines under transformer, the formula and how to compute for the voltage regulation is the same. And the procedure on how to compute for the vector sum of the voltages will still be the same, and we could use our knowledge on the so-called study of AC circuit, because under the study of AC circuit, alternator is actually related to AC circuit. So whatever we do under the AC circuit, we could do it on the alternator thing, right? That's why AC circuit is actually designed to compute the values under AC machines, just like on the so-called transformer and alternator. Actually, AC circuit is an application of the so-called transformer and alternator. Whatever the concepts on the AC circuit, we could use it on the alternator and transformer. So with respect to transformer and alternator, in the computation of the voltage regulation, the formula is actually the same, and the procedure on how to compute for the no load voltage is still the same. We still follow our knowledge of the AC circuit, okay, applied to transformer and alternator. Okay, I will try to read the problem. A 500 kVA, 2300 volt, 3-phase, star-connected alternator has a full load armature resistance drop per phase of 50 volts and a combined armature reactance, capital letter A with the subscript X. This is actually the reactance drop due to the excitation. Okay, this X here refers to the excitation drop, plus armature reactance E with the subscript ER. ER is armature, it's the reactance drop due to the armature drop. The combination of EX and EER is 500 volts per phase. Okay, calculate the percent regulation. Actually, the original problem got 3 unknowns, but we lack space on our magnetic board, so I just placed 2 unknowns. Calculate the percent regulation at unity power factor, meaning if this alternator, okay, has a connected load of 500 kVA on the terminals, the problem is asking what will be the percent regulation. How does the terminal voltage react? Will it be stable at a certain value, or will it be lower? Letter B, what will be the percent regulation at the load is 500 kVA and the power factor is 0.866%, lagging. Lagging meaning the load connected to the alternator are lagging. It could be all motors maybe. That's why it's a lagging power factor. If the load is are motors and the power factor is lagging, you expect there should be too much voltage drops on the alternator. There is, because motor loads actually consume too much current, and a big current corresponds to a big voltage drop. Okay, let's proceed with the solution of this one. The number 1 requirement here is we must have to draw the figure. We don't have to draw the physical thing of the alternator. We'll just draw the circuit diagram like what we did under AC circuit or AC machines under the study of transformer. Because the electrical diagram for a transformer and alternator is actually similar if we try to draw it in the magnetic board. So for a Y-connected alternator, meaning the armature that is rotating, cutting those magnetic plugs, okay, to generate voltage. Okay, if we try to bring out the circuit diagram of that one, it will be something like this. Okay, so for a star-connected alternator, this is now the simplified diagram, because the per-phase thing is it should be a complicated thing. It comprises of many coils, and each coil comprises of many turns, and those turns which are connected in series per phase represents the per phase winding. So these per phase winding are actually lots. This is the one creating the generated voltage, because a conductor is actually interacting with the magnetic plugs, whether we like it or not. It should generate voltage. That's the concept of a generator. There should be a magnetic plugs in alternator. No, any conductor. It's either that the flux is stationary, the conductor will be moving, or the conductor is stationary and the flux will be moving. But the conventional thing is, okay, the armature is rotating, the flux is steadily produced by the excitation thing, right? So we could produce a terminal voltage at the terminals. Like at the dam site, for as long as there is water on the dam, okay, propelling the turbine, if the turbine rotates, okay, it will rotate the armature of a big alternator, okay. When the armature of the alternator rotates due to the rotation coming from the turbine, okay, of course we generate voltage. That's why live water is actually very important in the so-called generation of electricity. We call that hydropower. A nuclear thing is different, okay? So the circuit diagram will be something like this. Star, right? So according to the given specification, this 2300 volts is actually the terminal voltage at the end of the three lines of the alternator. So this should be 2300, 2300, and 2300. This should be line number 1, line number 2, and line number 3. Between line number 1 and number 2, it's 2300. And between line number 2 and number 3, it's still 2300. And between line number 1 and number 3, it's still 2300. That's why we call it three-phase. Right? So this is actually the one going up to the transmission line now. But before we feed to the transmission line, we should step up the voltage 2300. We might multiply this by 18 times value. So it could rise up to the value 2300, maybe 20. It's 10 times value, that's less, 100 times value. So if we try to feed this to the transmission line, the voltage on the transmission line may be 230,000 volts. So if we try to transfer this energy for a long distance at a voltage of 2300, of course at the end of the line, we could still get some voltage. Because if this is small, and the delivery distance is too much, okay, of course your light will be gone before it will reach your house. So that's why from the alternator we step up the voltage to a certain value 2300, and this 2300, that's why transmission lines for the primary is very dangerous. That's high voltage. Right? Okay, let's continue. The given apparent power generated by the alternator, the rating of the alternator is 500 kVA. S is apparent power, right? Under the study of AC circuit, 500 kVA. This is still small because a big apparent power should be MVA, million volt ampere. This is 1,000 volt ampere. But this is just for an example problem here. Okay? The terminal voltage at the lines are actually 2300. ER is 50 volts per phase. ER is actually the, what you call this, IR trap. It is due to the resistance of the winding. And this EX plus EER is 500 volts per phase. This is the IX drop. Okay? This is the so-called voltage drop B sub R, and this is actually B sub X. B sub X, it refers to the reactance drop. It's the drop due to the reactance of the windings, the first one. And the second one is the first one is the the drop due to the resistance of the winding. Whether we like it or not, there should be a small resistance. That's why the IR drop compared to the IX drop is actually small. This is just 50, but this is 500. The problem is asking what will be the voltage regulation at unity power factor and at 0.866 lagging power factor. Okay, let's try to bring out the solution. To bring out the solution, we shall draw the vector diagram of the current and voltage per phase. Of course, there is a current coming out here, and so with here, and so with here, right? That's the current. And the relation of the phase voltage and current for a unity power factor, this is the voltage per phase, this is the current. At unity power factor, if this is the current, this is the voltage, they are in phase. Okay? There is no angle between them. That's why I drew from the vector diagram, this is the voltage per phase, and this is the current. They are in phase. There is no angle between them. In phase, meaning if the angle of the current is zero, the voltage, the angle of the voltage should also be zero. They are in phase, right? So this is now an application of trigonometry. This is a right triangle, right? Okay, let's try to bring out the solution. If the power factor is unity, this should be the vector diagram. This is the current. This is the voltage per phase on the alternator winding. They are in phase. And the draft due to the armature resistance is in phase with the phase voltage. This is a real part voltage. And the imaginary part voltage, the reactance drop is actually erected vertically. Okay? So this is horizontal, this is vertical, this is hypotenuse. We are on the study of trigonometry. Okay? We could compute for the voltage per phase. The voltage drop due to the armature resistance is given. And the voltage drop due to the reactance of the winding, reactance, it is given as 500 volts. It is not in phase with ER, it is vertically, B sub R and B sub X are actually, this is B sub R, this is B sub X, and the vector sum is actually the B sub Z. That's why B sub R and B sub X are not in phase. This is a real part, this is an imaginary part. This is E sub R, the armature drop due to the resistance. This is the drop due to the reactance. It is vertical, right? And we are given all these three here. And the vector sum is the right triangle. That's why we needed the concepts on the study of trigonometry to compute for the hypotenuse. This is actually the voltage per phase at no load. Okay? The one that we'll be using here. Okay? The first one. Voltage at no load. It is this. It is bigger than at full load because, of course, there is a voltage drop, right? Okay, let's try to compute for the voltage per phase. For a star connected, if this is 2300, we could compute for the voltage per phase. And the formula is this one. That's for a Y connection. Voltage per phase for a Y connection will be the line-to-line voltage over square root of 3, and that is 1330. This is 1330. Okay? The real part of the no-load voltage per phase is actually this portion here, plus this 50 volt. It is 1380. That's the real part. Okay? The imaginary part, okay, is this portion here. It is given as 500 volts. This is 500 volts. So if this is, we now know the value of this, 1380, and this is 500, it seems we are given a right triangle in which the two sides are given. We could compute for the hypotenuse. And the hypotenuse is actually the so-called voltage per phase at no load. So it will be, okay, we are given this and this. We use Pythagoras principle. Voltage per phase at no load now will be the square of this plus the square of this. Take the sum, then take the square root. What will come out will be 1468 volts. It is bigger than 1330, right? That is the voltage at no load. What's the significance of this? The meaning of this, the voltage per phase generated by the alternator should have a value of 1468 such that if we try to get our voltmeter and we try to measure the voltage over here, okay, it should come out 2300. That's the meaning of this. Okay, so the voltage regulation now will be by using this one. It should be 1468. Voltage at no load per phase is 1330 over 1330 times 100%. It is 10.36%. It's a little bit high. Why high? Because under the study of transformer, percent regulation is actually in the range 3 to 5%. Why? Because transformer has no moving part, right? And alternator has moving part, and there are lots of losses, right? That's the difference between a transformer and alternator. The only one moving for a transformer is actually the flux circulating. Okay, but for an alternator, there is a physical movement. It's rotating, right? That's why there should be many losses. So at unity power factor, the voltage regulation will be 10.36%. Okay, at 0.866 power factor, it will still be the same, but the what you call this, the vector diagram of the voltages will be different. It will be something like this. For at 0.866 power factor lagging, if this is the current at 0 degree, the voltage is actually at 30 degrees. Okay? This is the current, this is the voltage, and there is an angle of difference between them. They are not in phase. That's why it is 0.866 power factor lagging. This is the current, this is the voltage, and the angle between them is the given power factor. And we could compute for the voltage between the current and the voltage per phase. Just take the arc cosine of the given power factor. What will come out is actually 30 degrees. Meaning, for case number 2, for number 2 requirement, if this is the current, this is the voltage, the angle between them is 30 degrees. Meaning, as the current alternates, okay, the voltage will lag behind by a certain angle, 30 degrees. Okay, but pictorially speaking, this should be the diagram. Okay, this is the voltage per phase. So actually, there is a component for the voltage per phase. This is the horizontal component, this is the vertical component. Okay, and to add these voltages here, actually we could extend this one. This one is still same as that one. So actually we could remove this one. Okay, this portion here is actually voltage per phase sine of theta. And the first portion from here should be voltage per phase cosine, right? The horizontal component is cosine, voltage per phase cosine. The vertical component here is voltage per phase sine, is this cosine, this sine. And the drop due to the armature resistance is actually this one here, 50 volts. It is in phase with the real part of the voltage per phase, the one with the cosine of theta. And the other portion of the reactance drop is actually the given 500 volts. So if you try to see it, okay, there is an added component over here for the voltage drop due to the reactance. If the power factor is lagging, right? That's why the power triangle is bigger. This portion here is voltage per phase cosine of theta. This portion here is voltage per phase sine of theta. This portion here is actually the reactance or the drop due to the armature resistance. It is 50 volts. And this portion here is the given 500 volts. It is the drop due to the reactance of the excitation and the reactance of the winding. So this is 500 plus voltage per phase sine of theta, which is 665. Okay. The real part is 1,200 plus 50. What do you call this? No. It's not 1,200. This is 1150. This is 1150. 1330 times cosine of 30 degrees is 1150 plus 50 volts. The sum of these, they are both real. It is 1,200 volts. For the imaginary part, the vertical component, it is the sum of 100 voltage per phase sine of theta, which is 665 plus 500, and that is actually 1155 volts. The first one is 1,200. So it seems we are given a real part of 1,200, imaginary part of what you call this 1155, and the hypotenuse is actually the voltage per phase at no load. This is the total real part. This is the total imaginary part. If you try to see it, it's bigger, right? There is a component here added to the 500 volts at 665. So the voltage at no load will be the square of this plus the square of this, then take the square root. Okay, it is this. And what will come out will be 1665 volts. It is bigger than the 1468 because at lagging power factor, motor loads consume too much current. So there should be a higher current, and if there is a higher current, of course there should be a bigger voltage drop. So this is 1665, meaning at 0.866 power factor, the voltage per phase of the alternator should generate 1665. Okay, so that if we try to get our voltmeter and measure the terminal voltage, it should come out as 2300. It should generate more if the motor loads is actually, if the loads are actually motor loads. So the percent voltage regulation now will be 1655, or 1665 minus 1330 over 1330 times 100%. And the voltage regulation is 25.8%. This is high. Okay? Alternator got a very hard work to generate voltage. If the motor loads, if the loads are actually motor loads. That's why sometimes utility companies want us to shut down our, what they call this, air conditioners during peak hours because the transmission lines are actually overloaded, or the alternator could be overloaded. Okay, that's it, guys. This is Professor David J. Good morning from Los Angeles.